All right, welcome back. Today we are talking about 6.3, which is all about focusing on triangles. So as we know, a triangle is just a three-sided polygon, which really just means a shape made up from three straight lines that is closed. Now, we've already talked about this, but just a reminder that all of the interior angles, the angles made inside of a triangle, will sum to 180. And we've discussed this in our last lesson about angles. Also, to kind of refresh our minds, the word congruent. Congruent means the same shape and the same size. So we can talk about congruent side lengths. And when we talked about congruent side lengths before, we talked about more so congruent line segments, but those can be identified using matching tick marks. Congruent angles we've talked about before as well, and these are identified by using matching curves. So whether there's one curve mark or two curve marks, and we'll see that notation come up again even as we talk about triangles. So just looking in the diagram below here, I can see I have a triangle, a three-sided polygon. Based on this, I can see that these two side lengths, this pink one over here and this pink one over here, are congruent because I can see they have equal markings on both sides. The third side length would not be congruent to those two pink ones because I can see it is lacking those markings. When I'm talking about angles, I can see I also have two congruent angles. This one and this one that I've kind of highlighted or outlined in purple because, again, I have those equal markings on both. That third angle is not equal because I don't have any of those equal markings on it. All right, so we are going to jump into talking about specific types of triangles. There's kind of four of them that we're going to talk about. The first one is equilateral triangles or equilateral. Now, for some of you, you might have heard the word lateral before, particularly if you ever done like a workout in the gym. That's where I hear it most often. Lateral means side. So I might be doing like a lateral arm raise. That means I'm lifting my arms to the sides of my body. If I'm doing a lateral jump, that means I'm jumping to the side. So lateral implies side, kind of sounds like equal. So an equilateral triangle means that all of my sides are going to be congruent or equal in measure. What happens with triangles is whenever I have equal sides, it always comes with equal angles. And this is something specific to triangles. So if all my sides are going to be congruent, then all of my angles are also going to be congruent. So I can see in my equilateral triangle diagram, I can see that all sides are equal here because I can see they all have the same markings. And all of these angles are also equal because they also have the same markings. Now, we talked about angles in a triangle summing to 180. And if all three angles are the same, I can just say, okay, well, each angle is 180 divided by 3, which is exactly 60 degrees. So without knowing anything else about an equilateral triangle, other than the fact that it's equilateral, I know that that angle and every single angle in that triangle will measure exactly 60 degrees. Okay, next type of triangle is an isosceles triangle. Now, an isosceles triangle has two of the sides being congruent. And like I said, sides that are congruent will always come with angles that are congruent. So if I have two of the sides congruent, I'm going to have two of the angles that are also congruent. And these angles are located across from these sides. So two of the sides and the angles located across from the sides, I'm missing the word here, are congruent. So here I have one side and the angle across from it, or sometimes we say angle opposite from it, is this guy. Here I have the other side that's congruent to the one I've highlighted in pink. And the angle across from it is this one. So sometimes we say across, but I'm also going to write in opposite, because this is the language that we'll use primarily next year when we talk about some cool triangle stuff. Okay, so we've got equilateral, all three congruent. Isosceles, we've got two congruent. Scalene is the next one, and this means that we have no congruent sides and no congruent angles. So all of these angles will be a different measure. And I could denote that by having three separate symbols, separate amount of curves on each of those angles. I could do the same thing. So here I might have three sides, and I could denote them with three separate tick marks or types of tick marks, because I can see that none of these sides and therefore none of the angles will be congruent. The last type of triangle is a right angle triangle. Now, fun fact, a right angle triangle can technically be isosceles. A right angle triangle could technically also be scalene, but a right triangle could never be equilateral. Do you know why? Of course you know why. Because in a right angle triangle, I have one right angle, and a right angle measures 90 degrees. But in an equilateral triangle, all of our angles should measure 60 degrees. So just by definition alone, I can't be equilateral because it's not possible to have a 90-degree angle in an equilateral triangle. Okay, so you've actually seen right angle triangles before, and you've actually done a bit with them, calculation-wise, in previous grades. So before, you used something called the Pythagorean theorem. Some teachers pronounce it Pythagorean theorem, and both are fine, however you wish. But this theorem helps me find side lengths of a right angle triangle. It only ever works for right angle triangles, which means if I have isosceles, I have equilateral, I have scalene, and those triangles do not have a 90-degree angle in them, I am not able to use it. But if I do have a right angle triangle, here is my theorem. My theorem talks about side lengths. So if I have a side length in my triangle that I am missing, I can substitute the values that I know in the other two positions, and I can solve that equation. The really big and most important thing about that Pythagorean theorem is side C must always represent the hypotenuse, which is defined as the longest side. Now, that longest side is always going to be located across or opposite to the right angle. So it doesn't matter what orientation I rotate that triangle. So maybe I take that picture and I put it upside down. Maybe I take that picture and I flip it over and rotate it 35 degrees to the right. Doesn't matter. If I know where that 90-degree angle is located, then the hypotenuse will always be the side length across from or opposite that right angle. And that number must always go in the C position. That hypotenuse is always going to be the longest side. Now, fun little fact about triangles. Now, when I name a triangle is typically named based on the capital letters that exist as its vertices. And remember, vertices is just the plural of vertex. But a vertex is just a point that's located at the corner. So if I had my triangle here, I have 3 points and I've played connect the dots with, and I've built this triangle. Now those corner points, just like all points, will always be labeled with capital letters. Now the cool thing about triangles is technically I can name its sides based on like a line segment naming. I can call this segment or line segment AC. But mathematicians are like, okay, look at this. Triangles, they're a pretty common shape. We can do some pretty cool math stuff with it. So I wish there was a little bit of a shortcut on ways that I can name it. Something that takes me a little bit less time to write down. And there is. And the rule of thumb is, if I take any angle, let's say I take angle A, the side that's located across from it, I can name lowercase a, or little baby a. And I could do that for every single angle. So if I take angle C, the side opposite or across from it will be little baby c. And if I take angle B, the side opposite it will be little baby b. And the reason that we say the side that's opposite from it is because if I set the side beside it, well, there's technically two sides to every angle, right? There's a left and a right. I don't know which one's the one I'm talking about if I was saying beside the angle. So we always say across from. So when I take a look at this is one way to go ahead and name my side lengths of a triangle to be a little bit more simplistic. All right, so let's take a look at these three triangles. We're going to find the missing lengths. But before we even start, I want you to take 2 seconds to do two things. Okay, thing number one is I want you to write the name of each of the sides. Using this method we just talked about at the top here, I want you to label the sides using lowercase letters based on the angle name across from that side. The second thing I want you to do is I want you to highlight the hypotenuse of every single triangle on this page. Pause the video, try it out. All right, welcome back. So I'm taking a look at these and I'm simply going to do those two things. Thing number one, I'm going to rename this triangle with the side lengths. So I know side length E will be opposite angle E. Side length F will be opposite angle F. And side length D will be opposite angle D. And for my hypotenuse, that's the one across from or opposite to my 90 degree. So if E is 90 degrees, then my hypotenuse is little e. Okay, I'm only going to do one triangle at a time because we'll go through the rest of it as we go as well. But this is what I've got. The first two examples we can do without a calculator. I'm trying to find the missing side length. So I know my Pythagorean theorem or Pythagorean theorem. I always get tongue-tied with that word. And it's this guy here, a squared plus b squared is equal to c squared. And I don't have a, b's, and c's, but it doesn't actually matter. What matters is that hypotenuse, the one we just highlighted, has to go here. So whatever value e is has to go in that position. The other two values, kind of a dealer's choice. I'll put 12 in b and 5 in a. But quite honestly, they don't matter because I'm just adding them together and the order of addition doesn't make a difference in my final answer. So I've got 5 squared plus 12 squared and I get e squared. It is so very important that we are using, oops, that wasn't a highlighter, e as our unknown rather than c. And why is that? Because we have no c in the question. And sometimes we have a side length named c, but it's not the hypotenuse. Okay, so c, just because something's named c, doesn't mean it goes in the hypotenuse spot. We always just want to make sure we're using the numbers or variables already introduced into my question here. All right, now we're going to do some math. 5 squared, it's just 25. 12 squared, that's 144. And e squared, I can't do anything. Just like before when I'm solving equations, I'm trying to simplify each side before I do any other reverse operations. So I'm going to keep on going. 25 and 144, well, that's 169, which is e squared. Now, as I mentioned, we try and simplify as much as possible before we isolate for our variable. And I can't do anything else on the left. So I'm going to undo the exponent. I undo squaring something by square rooting something. So I get e alone on the right, and the square root of 169, well, that's just 13. That's one of the perfect squares that I know. And of course, we talked about the order of the answer, always having the variable first. But the next thing I want to talk about is units. In this particular question, I'm taking e being 13 as a measurement, the length of a side. And because all of my measurements in this particular question was in kilometers, then my answer should also say that e is 13 kilometers long. And this is what I get. Now, some of you might be asking, Miss T, do you have to show all the steps? And the only step that's kind of optional here is this first one. You don't have to write out the Pythagorean theorem without the substitution in there first. You're welcome to, but you do not have to. Everything else, I would say, is pretty necessary. Okay, moving on. So in the next example, I'm going to start by labeling all of the sides. So across from angle B is little baby b. Across from angle C is little baby c. And across from angle A is little baby a. Now I'm going to name or label the hypotenuse. And we said the hypotenuse is always opposite the 90-degree angle. So if B is the 90-degree angle, the hypotenuse is little b, which is 15. And this is why I want to point out the Pythagorean theorem and how C's aren't always the hypotenuse, and why this value here has to be the hypotenuse when I plug it in. And the hypotenuse we know is little b. So it's so incredibly important that when we have a triangle that's labeled A, B, C, that we don't just automatically put in values that are in those spots. Okay, we need to make sure we're thinking about it critically every time. So I know that instead of c squared, I'm going to put 15 squared. That's 2 looks kind of like a number. There we go, 15 squared. And then dealer's choice. I can put the value of c in the spot of A. I don't know what it is, but that's okay. And I could put the value of 9 in the spot of B. The only thing that matters the most is that I put my hypotenuse in the spot of my c squared. Okay, now I do the math. When we are solving equations, remember, we're trying to simplify both sides first. So I know 9 squared is 81. I know 15 squared is 225. And I've simplified both sides as much as possible. Now I want to get my variable alone. I do that by subtracting 81 from both sides first. And I get c squared is equal to 144. And again, I can undo square with a square root. If I do it to one side, I have to do it to the other. And I get c is equal to 12. Remembering that I need to have my units. In this particular example, my units are measured, or my side lengths are measured in meters. So my final answer will also be measured in meters. So one of the big things that I'm talking about in this section that we maybe forgot about, or that's really, really important that we remember now, is that we need to make sure the hypotenuse always goes into the C spot. Always, always, always. The second thing we learned today so far is that we can name triangles based on the angle names or the vertice names. We have this last example. Now, this last example, we need to use a calculator for. But it's also a little bit special. Why is it a little bit special? Because you might look at this triangle and go, Miss T, oh my goodness, I'm not given 2 of the sides. I don't know which side which side I'm solving for. I don't know 2 of the 3 sides to solve for the third one. I am freaking out. But you also might notice that there's these little tick marks on each of the sides, which means whatever one is equal to, the other one is also equal to. So let's not jump ahead of ourselves. Let's start by naming the sides of this triangle. I know across from angle H is little baby h. I know across from angle I is little baby I. And I know across from angle G is little baby g. I know the hypotenuse is always across from the 90-degree angle, so little h must be the hypotenuse. And if I were writing out the Pythagorean theorem with all the values I know, I'd go I squared plus g squared is equal to 10 squared. Okay, this is great, but again, how do I solve for two things that are unknown? Well, here's where isosceles triangles and those tick marks come into play. Because I know that I and G are congruent. They are the same shape and the same size. I can say the size of, so here's them being congruent. The size of that side, the length of it, the measure, the actual number associated with it will be the same. So I know the number associated with I will be equal to the number associated with G. Now, this might rack our heads a little bit, but I am going to say, well, if G and I are the same thing, why don't I just call them the same thing? So instead of saying I squared and G squared, why don't I say I squared plus I squared? And again, I am doing this because I know the value of that side length, whatever number is in the spot of that little I, is going to be identical or equal to that number in the spot of the little g. And I'm going to finish this off. Now, when we were talking about solving equations, we needed all of our stuff to be together, all of our variables to be lumped into one. Just like I have 1i squared and 1i squared, together they simplify to give me 2i squared. And my 10 squared, I'm going to replace with 100. So I've done two things. I've collected like terms, and I've done some math here. All right. Now I want to get I alone. There's two things happening to it. It's being multiplied by 2, and it's being squared. I have to go through and do reverse BEDMAS. So I have to undo the multiply by 2 by dividing by 2 first. So I get I squared is equal to 50. And then I'm going to undo the square by square rooting both sides. Now, this question said I can use my calculator because 50 is not one of those perfect squares. I'm not expecting to know it. But something that I will point out, because I've estimated square roots before, I know the square root of 50 is really, really close to the square root of 49. And the square root of 49 is 7. So the square root of 50 must be like 7.1-ish. And if I do the math and round to the nearest tenth, like this little speech bubble tells me to, I actually find out that it actually is 7.1. Again, I need to go back and say, look, what are my units? My sides were measured in centimeters, so my new side I've calculated is measured in centimeters. So I know what I is. And because I know I and G are congruent, meaning they're the same shape and the same size, G will also be the exact same number. Okay. That is it. That is all. There is some practice that follows, so please make sure that you work on that practice. But otherwise, have a lovely rest of your day. Bye.